Right, so today we will basically discuss complex graph representations, what data we can represent on graphs, what basically are graphs used for. Usually what most people use graphs for are multi-component systems. So you have, for example, a physical problem that you have too many particles and you want to represent this. You can view each particle as a single problem, basically as a single independent individual. So that's what usually most machine learning algorithms do. They look at, for example, coordinates of your molecule, and based off of that, they do basically some calculations. Now, when we use graphs, we look at these particles and their interactions, and we look at this structure all at once. We don't basically separate each point and look at them basically individually. So basically what happens is that we are incorporating these interactions that molecules have with each other into our basically problem, and that will leverage basically we are basically leveraging that into a better solution. Now, we can represent different types of data on using basically these graphs. For example, these nodes are our particles, and these edges are showing the relationship between these two nodes. So they can show proximity. They can show if two nodes are physically close to each other, if they are interacting with each other, if they are having a basically specific type of relationship with each other. So we can represent it with whatever that is important for our problem. Graph deep learning is basically right now on the frontier of deep learning. They're doing some very amazing problems. Very recently, less than a year ago, this paper came out from DeepMind. The model was called AlphaFold, and it was using deep learning to predict shapes of proteins. So proteins are essentially long molecules. They're a chain of amino acids, and but in your body, they do basically engage in different actions, and they result in different metabolisms in your body. For example, when you get sick, when you have a drug and you get basically better, or any other natural functions that your body has. So, but they don't just stay like a string. They tend to fold and find the final shape. And that final shape is essentially determining what type of action they're having. So it's a very important problem. If you can have that protein and you can find its final structure, and it's a very important problem. People have been working for decades to find, given the basically amino acid sequence, know the final structure, final 3D shape of that protein. And recently, DeepMind has solved it with a high accuracy of 90%. And it's interesting to know, this model is AlphaFold 2. The previous one, AlphaFold, which was also very pioneering, was only able to solve it by 55% accuracy. So it has been a huge leap in the past couple years, just by using basically deep learning models to solve a problem. So it is a very important tool that people are right now trying to use it for different tasks. Graphs and networks are not very new, but not very old. People have been studying large graphs since 90s. This group, basically Albert Barbashi from our own university in physics department, was one of the people that started the field. So when he's the writer, the author of one of our textbooks, and in its introduction, he says that when I was starting, no one was funding this research, so the field was non-existent. And this paper, for example, was published in Nature in 1999, and no one was funding him because he basically had to prove that, this is actually a very important problem. And he basically has entered an interesting introduction, and he basically explains when he was commuting between Chicago and Notre Dame, he was just thinking about how you can use networks and graphs to represent complex systems, and you use that to solve problems, use basically their relationships. So I'm going to go over a number of cases where you can use graphs to represent things, and basically people are using it. One example, probably many of you have heard of, are molecular graphs. So in molecular graphs, you're representing each single molecule using a graph. In this representation, you have nodes that are representing atoms in the molecule, and you have edges that are representing covalent bonds between different atoms. So now we have next amino acids that basically I mentioned that they are long molecules and they are constructed of a chain of amino acids. You can consider, for example, each amino acid as a molecule, as basically a node, and their spatial proximity as the edge between them. So that edge essentially shows that if two amino acids are close to each other and probably are interacting with each other. Social network. So before internet was a thing, sociologists were studying social networks without the context of these websites as the type of interactions that you people have with each other. Friends, families, students, teachers, and different basically type of things. It was very important for many reasons. For example, one that you can relate with is spread of disease. They use this to figure out how disease spread, especially in 90s with HIV epidemic, 80s. So the other thing is internet and World Wide Web. So people use these two interchangeably, but internet is actually the physical connection between computers. So when we represent internet with a graph, my computer is a node. The cable that connects this computer to wherever the other website is, that basically it is physically stored, that cable is the edge, and that other computer is another node. When you talk about World Wide Web, you're talking about each website as the nodes, and the hyperlink that you click, and it takes you to another page. That's going to be your edge, and that another page is going to be another node on that graph. So this is a figure of nd.edu graph in 1999, but it's just the first 2,000 basically pages. It took 3 days to run the whole thing. It was more than around 1 million nodes, edges, and at the end of the day, it was just a blue circle. So because it has so many nodes. So transportation network, you can study transportation and flow of traffic by assuming that traffic and basically the transportation system is a graph. You can look at roads that take you from one city to the other as edges, and you can look at the intersections that connect these roads with each other as nodes. fMRI data. So our brain has different regions. These regions work whenever you're doing different tasks. So some of these regions work together. Some of them don't work together. So people use fMRI to study what regions of brain are doing what. And when two regions, for example, this green region and this other green region, are working at the same time, it means that these two are related to each other. So the guy is writing and two different regions of brain are working. It means that these are correlated. So the temporal activity correlations are represented by edges in this graph. And it is basically used to analyze these data. Or simulations, we can represent, for example, our CFD simulations using nodes and edges. So again, why graphs? So you can do everything that you do with graph neural networks, with or graph machine learning in general, with regular ones. You can, for example, if you're studying a molecule, you can feed the 3D information of that molecule as our input signal and give it to some, for example, we call it F, some machine learning algorithm, and it takes that and it turns it into basically something that you want. So for example, you have a set of molecules, you train a model in order to basically map the input coordinates, 3D coordinates, into output properties. For example, if whatever basically chemical property that you want. Graph neural networks don't look at the coordinates, or at least they don't look at the coordinates only. They look, the main thing that they look is the atoms and their connections. So they look at this, at the whole graph, and they leverage these connections to find a better basically accuracy for their basically, solve the problem with a better accuracy. Now, so how graphs are different, how graph machine learning is different from others? Why we need a whole new bunch of stuff to study graphs? Can't we just use whatever we had before? The answer is simple. So consider these two graphs. On right, you have a grid. Let's say that we want to do some convolution on this. We define this window, we slide this window at each basically, we slide this window one grid by one grid, and we do some computation on this. So for example, we average all the nodes in this square, and then that's gonna be our output, a single output. And then we move on to the next one and do the same, and again, the next output. But now let's do that on this graph. It's not possible. Why? Because there is here, we could have slide left or right or up or down. There was a basically meaning to that. There is no meaning to right or left or up or down here. So you can't basically, you basically have to select 9 points at random. The next one doesn't have 4 neighbors, has 10 neighbors. You don't know where is left, where is right. So for that reason, we need tools to extend our analysis on Euclidean domain to this new non-Euclidean domain. As I mentioned, we are going to look at this in basically on 3 levels. We're going to look at the traditional methods that people were using before this whole machine learning and deep learning thing came out. Then we're going to look at, so that's more mathematically basically motivated. Then we're going to look at the learning on graphs without any deep learning. So essentially to create features on graphs and just having the feature without doing any deep learning to study it for whatever reason. Then at the end, we're going to go on graph-based deep learning. So in graph-based deep learning, you're going to build layers that are going to be a transition from the graph that you have to some sort of basically numerical vector that regular essentially fully connected layers of your whatever basically vanilla deep learning model is able to analyze. So let's start with some definitions. Graphs are constructed of nodes, a set of nodes and a set of edges. So you have these basically nodes here that are connected pairwise with some edges. Some of them are connected, some of them are not. So they have different names based off of the field that basically that book is coming from. If you're studying some sociology book, it's probably calling graphs networks. And if you're reading a physics book, it's probably calling nodes sides, and it's calling bounds and edges bounds. So they have different names in different fields. Nodes, vertex, side, actor, all means the same. Edge, link, connection, bound, and tie and interaction. all again means the same. It means that a pairwise connection between two nodes. Now, we have two sets of two general type of graphs. Our graphs are either directed or undirected. If we're dealing with an undirected graph, it means that these two nodes are only connected to each other, and there is no basically direction in this graph. So two nodes are connected to each other. If we have a directed graph, we have a direction. So it means that the edge is defined as an arrow from one node to the other. We usually use the second index as the starting one. So here, no, basically this is represented by V1, V7. In undirected graph, both of these mean the same thing. If I write V1, V2, it means V2, V1, because they're the same thing. Now, we need to represent our graphs using some mathematical notion, in order to be able to do some algebra basically on that. What people, the most basically famous matrix is essentially adjacency matrix, which is defining using a matrix to represent this undirected here. Let's start with undirected first. So let's say that we want to represent this graph. We select the number of nodes. Here are 7, and we enumerate this. We enumerate this and generate a matrix which is 7 by 7. And then, for example, here I want to represent this edge, 5 and 2 are connected to each other. So here it means that the 5th row and 2nd column, this element is going to be shown by 1. Because this is undirected, this means that row 2, column 5 is also 1. So everything else in this matrix is going to be 0. So we're representing this with 1s and 0s, and that's going to be called adjacency matrix. Now, it doesn't really matter how you basically enumerate these nodes. It just matters that you correspond each basically row and column with one of these nodes. Then we have adjacency matrix for directed graphs. So in directed graphs, in the previous one, we were dealing with a symmetric matrix, because if node 1 and 2 are connected, it meant that 1 are connected, 1 and 2 are connected, they had the same meaning. Now, here, it does not have the same meaning. So again, the convention is to have node Vn defined as the arrow, basically the edge that goes from node N to node M. So, for example, here, we have 1 and 7. This means that it's starting from 7. So this is going to be 1, and this guy is going to be 0. So this is not necessarily symmetric. It can be symmetric if we have edges on both ways, but it's not necessarily symmetric. Another important concept is degree. Degree of each node means the number of incident edges to that node. So for example, here, look at node 3. Node 3 has 1, 2, 3, and 4 edges connected to it. We can compute this by just looking at the adjacency matrix. So when we are looking at the edges that are connected with 3, we are representing that with 1. So if we look at the 3rd row or 3rd column, because it's an undirected graph here, we will see that if we sum all these values, it's going to be your degree. It's going to give you the number of edges that are connected with that node. We have the same concept defined on undirected graphs. So for that, we will have two definitions. We will have in degrees and out degrees. For in degrees, we are going to sum basically the row corresponding to that node So here there are no basically edges pointing towards V3, and there is basically the sum of row 3 is 0. For the out degree, we're gonna sum all the elements on a vector corresponding to that node. So here we have 4 out degrees from V3, and that is shown used by that basically can be derived by summing all the elements on the 3rd column. Now, degree matrix is another type of representation you can use to represent a graph, and that is a diagonal graph, basically. For an undirected graph, that's a diagonal matrix whose diagonal elements, for each element corresponding to each node, is just the degree of that node. So for this graph that we looked at, the first element is going to be 2. The 3rd element here had 4 neighbors, 4 basically connections. It's going to be 4, and so on and so forth. So only diagonal elements are represented with their degree. Everything else off diagonal is going to be represented with 0. So now we have sometimes some information that we want to represent with our graph. So here, for example, we have a molecule, but each node is not representing the same atom. Each one is representing a different atom. So we need to distinguish these nodes. So we do that by basically representing some type of node features or node attributes on each node. And we can do that for discrete information, like the type or categories, or for regression type of problem. For real values. So here you can see that we have an alanine dipeptide molecule. It consists of 4 types of atoms. It is oxygen, nitrogen, it has carbon, and it has hydrogen. So when we want to represent these information on this graph, we basically construct a one-hot vector, which means that it is a vector of length of whatever basically number of categories that we have. So here we have 4 categories, which are representing the type of atoms that we have. And for each atom, we set the corresponding 1 to 1, and everything else to 0. So if I'm representing this atom, which is an oxygen, I'm setting the second element to 1, and everything else is 0. So that is the type of feature I want to represent. And we can represent that on each element on the graph. We can use graphs to show real values, to basically use the graph as a domain to represent real values as well. So for example, we have these real values corresponding to different nodes in this graph. And this graph now is defining a map from the node domain to an n-dimensional vector, where each element of the vector is going to be basically the real value corresponding to the node in that element.